is a limit to how far you can see, not a limit of telescopes or of money or of patience, a limit built into the structure of reality itself. Point the finest instrument ever built at the darkest patch of sky. Leave the shutter open for weeks, and you will collect galaxies by the thousand, smaller and fainter and redder the deeper you go. Keep going, and eventually the galaxies stop. Not because space runs out, because time does. Beyond a certain distance, light has not had enough time since the beginning of the universe to reach us. Whatever is out there is real, and it exists right now, and it will never be visible to anyone standing where you are standing. We call this boundary the edge of the observable universe. It sits about 46 billion light years away in every direction, and it is not an edge in the way you might imagine. There is no wall out there. Nothing changes at that distance. If you traveled to it, you would find ordinary galaxies going about their business with their own horizon around them and yours far behind. It is a horizon in the truest sense, like standing on a beach and looking out to sea. The line you see is not the end of the ocean. It is simply the point where the shape of things hides the rest from you. Tonight, we travel to that boundary. We find out why it is further away than the age of the universe should allow, what happens at the very last visible layer, and how much of the cosmos we have already lost forever. If you find calm in the vast, unhurried scale of the universe, consider subscribing to the channel. Let the enormous distances carry your mind somewhere quiet as we drift together toward the edge of sight. Welcome aboard, astronaut. Tonight, we drift through the cosmos. We lift away from Earth and keep going. The moon passes. The planets fall behind. The sun becomes one star among many, then one star among billions. And the Milky Way spreads out beneath us as a great glowing spiral. We keep rising. Andromeda drifts by. The local group shrinks to a scattering of lights. The filaments of the cosmic web unfold around us, luminous threads of galaxies stretching in every direction, with vast dark hollows between them. And still, we keep going. The galaxies around us change. They become smaller, more irregular, bluer at first, and then progressively redder as their light stretches. They look younger because they are younger. We are not only traveling outward, we are traveling backward. Eventually, the galaxies thin out and disappear, and something else takes their place. A uniform glow, filling the entire sky in every direction, arriving from a time before any star had formed. That glow is the furthest thing light can ever show us. Tonight, we will reach it. On the way, we will learn why distance and time are the same measurement out here, why some galaxies are moving away faster than light without breaking any rule, and why the sky is dark at night. We will find out how much of the universe we can never visit, whether the whole thing is finite or endless, and what happened in the first fraction of a second to make any of it possible. Settle in. Let your breathing slow. We are going as far as anyone can go. Let us begin with the number because it does not seem to make sense. The universe is about 13.8 billion years old. Light travels at a fixed speed. So the obvious conclusion is that we should be able to see out to about 13.8 billion light years and no further. That is not the answer. The actual radius of the observable universe is roughly 46.5 billion light years. The observable universe is more than 3 times wider than its own age allows. And nothing in that statement violates any law of physics. The resolution is expansion. When light left a distant galaxy 13 billion years ago, that galaxy was relatively close to us. The light began traveling toward us across a modest gap, but space itself has been stretching the entire time, and every stretch added new distance to a journey already in progress. Picture an ant walking along a rubber band while somebody slowly pulls both ends. The ant moves at a steady speed relative to the rubber beneath its feet, but the rubber keeps growing. When it finally arrives, the total length it crossed is far greater than the length it started with. Light is the ant. Space is the rubber band. So a photon that traveled for 13 billion years did not cover 13 billion light years of present-day distance. It covered far more because the ground it was crossing kept expanding beneath it, and the galaxy that emitted it has been carried along by the same expansion. It is not where it was. Today, it sits tens of billions of light years away, far beyond the reach of anything we could ever send. Now, let's go deeper into what expansion actually is, because it is almost always pictured wrongly. Galaxies are not flying apart through space like debris from an explosion. There was no central point, no blast, nothing rushing outward into an empty region waiting to be filled. Space itself is getting larger, everywhere all at once, uniformly. The distinction matters enormously. In an explosion, there is a center, and things nearest the center move slowest, and there is an outer edge with nothing beyond it. The universe has none of these features. There is no center of expansion and no boundary that the expansion is expanding into. A common way to picture it is the surface of a balloon covered in dots. Inflate the balloon, and every dot moves away from every other dot. No dot is the center. No dot is moving across the rubber. The rubber between them is simply increasing. And here is the crucial consequence. The further apart two dots are, the faster they separate, because there is more rubber between them to stretch. That is exactly what we observe. A galaxy twice as far away recedes twice as fast. The relationship holds across billions of light years in every direction, and it has been measured with increasing precision for a century. It also means the expansion is not something happening far away in deep space. It is happening here in this room right now. But on small scales, gravity and the forces holding matter together overwhelm it completely. Your body is not expanding. The Earth is not expanding. Even our galaxy is bound tightly enough to ignore it entirely. Only across the vast empty gaps between galaxy groups does expansion win. But that's not all, because measuring how fast it expands turned out to be extraordinarily difficult. To measure expansion, you need two things for the same galaxy: how fast it is receding, which is straightforward from its redshift, and how far away it is, which is not straightforward at all. Distance in astronomy is built like a ladder, with each rung depending on the one below it. The bottom rung is geometry. As Earth orbits the Sun, nearby stars appear to shift very slightly against the distant background. Measure that shift, and simple trigonometry gives the distance. A dedicated spacecraft has now done this for well over 1 billion stars. The next rung uses a special kind of star that pulses in brightness at a rate set by its true luminosity. Time the pulse, and you know how bright it really is. Compare that with how bright it appears, and the distance follows. These stars are bright enough to be picked out in other galaxies. The top rung uses a particular type of exploding star that always detonates with almost the same intrinsic brightness. They are visible across billions of light years, and they extended the ladder into the deep universe. Each rung is calibrated against the one beneath it, so an error anywhere propagates all the way up. And there is a genuine problem at the top. The expansion rate measured this way disagrees with the value calculated from the oldest light in the sky. The two numbers differ by around 8%, and the uncertainties are now small enough that the disagreement cannot be dismissed. Nobody has resolved it. It may be a subtle measurement error. It may be something missing from our model of the universe. But what happens when we point a telescope at that expanding space? We see the past, always, without exception. This is true even close to home, but the delays are so short that we never notice. The moon you see is 1¼ seconds old. Sunlight is 8 minutes behind. Jupiter is around 40 minutes stale. The nearest star is 4 years in the past. The center of our galaxy, 26,000. Andromeda, 2.5 million years. Push further, and the effect stops being a technicality and becomes the entire point. A galaxy 10 billion light years away is not merely far. It is 10 billion years young. We are not seeing what it looks like. We are seeing what it looked like when the universe was less than 1/3 of its current age, and there is no way to find out what became of it. Astronomers have a phrase for this. Looking out is looking back. It is also the only reason cosmology is possible at all. We cannot run experiments on the universe. We cannot watch a single galaxy grow up because that takes billions of years. But because distance is time, we do not have to. We can photograph galaxies at every stage of cosmic history simultaneously simply by looking at different distances. Nearby galaxies show us the present. Middle distances show us the Middle Ages of the cosmos. The furthest objects show us the beginning. The night sky is not a picture of the universe. It is a diagram of its entire history, arranged in layers, with the oldest layer furthest out. And yet, there's more to this story, because we need a way to measure that depth. The tool is redshift, and it comes directly from expansion. While light is in transit, space stretches. The light stretches with it. Its wavelength grows longer, shifting it toward the red end of the spectrum, and for the most distant objects, well past red into infrared. The amount of stretching tells us how much the universe has expanded since that light departed, and because we know how expansion has proceeded over time, that translates directly into a distance and an age. Redshift is measured with a number. A redshift of 1 means the light has been stretched to twice its original wavelength, and the universe has doubled in size since it was emitted. A redshift of 9 means 10 times. The most distant galaxies confirmed so far sit beyond a redshift of 14. Their light left them when the universe was less than 300 million years old, roughly 2% of its present age. This is why the newest large space telescope was built to see infrared. Visible light from the early universe does not arrive as visible light. It arrives stretched into the infrared, invisible to eyes and to ordinary cameras. To see the first galaxies, you must build an instrument that sees heat and then keep it extraordinarily cold so its own warmth does not blind it. The results have been genuinely surprising. Those early galaxies are brighter, more numerous, and more developed than most models predicted for such an early era. Explaining how they assembled themselves so quickly is currently one of the more active arguments in astronomy. And yet, there's more to this story, because the way we learned to look this deep began with a gamble. In 1995, the director of the Space Telescope Institute made a decision that many astronomers considered reckless. Time on the Great Orbiting Telescope was desperately scarce. Proposals were reviewed fiercely, and every hour was fought over. The director held a small personal allocation to be spent at his discretion. He chose to spend 10 consecutive days staring at nothing. He selected a patch of sky in the northern constellation of the Great Bear, chosen precisely because it appeared empty. No bright stars, no known galaxies, no interesting objects of any kind. A blank window, small enough that from the ground it would be covered by a grain of sand, held at arm's length. Critics pointed out the obvious risk. If the patch really was empty, 10 days of the most valuable telescope time in existence would produce a photograph of darkness. Over 300 separate exposures were taken and carefully combined. The image came back covered in galaxies, around 3,000 of them, in a piece of sky representing roughly 1 part in 24 million of the whole. Spirals, ellipticals, irregular fragments, many of them so distant that their light had traveled for most of the age of the universe. It changed how people understood the sky. There is no empty direction. Point anywhere, expose long enough, and the darkness fills with galaxies. Deeper images followed over the years, each one finding more. And the arithmetic that follows from them is how we arrive at the estimate that the observable universe contains something like 2 trillion galaxies. The journey continues to the furthest thing light can ever show us. Keep looking outward past the earliest galaxies, and eventually you run out of galaxies entirely. Before the first stars formed, there was nothing shining to photograph. But there is still something to see, and it fills the whole sky. For the first few 100,000 years, the universe was hot, dense, and opaque. Matter was ionized. Electrons roamed free rather than being bound into atoms, and free electrons scatter light relentlessly. A photon could travel only a tiny distance before being knocked in a new direction. The early cosmos was a glowing fog, bright but impossible to see through, in exactly the way you cannot see through a cloud. Then, about 380,000 years after the beginning, the expansion had cooled everything enough for electrons to combine with nuclei into neutral atoms. The free electrons vanished, and the fog cleared everywhere in a relatively short interval. At that instant, the light that happened to be traveling in our direction was set free, and it has been traveling ever since. That light is still arriving. We call it the cosmic microwave background, and it comes from every direction with almost perfect uniformity. It has been stretched enormously on the way. It left as a fierce orange-white glow comparable to the surface of a cool star. 13.8 billion years of expansion have stretched its wavelength by a factor of about 1100, dragging it down into the microwave band and cooling it to less than 3 degrees above absolute zero. It is the oldest light in existence, and it is genuinely a wall. Not a physical barrier, but the boundary of what any telescope can ever detect. Now, let's go deeper, because there is something on the other side. We cannot see past the wall of light, but light is not the only messenger. About 1 second after the beginning, long before the fog cleared, the universe became transparent to something else. Neutrinos. Neutrinos barely interact with anything. That makes them almost impossible to detect. But it also means they escaped from the dense early cosmos when everything else was still trapped. A background of these ancient neutrinos should fill the universe today, cooled by expansion to a fraction of a degree above absolute zero. We are reasonably confident it exists, because its gravitational influence shows up in the structure of the cosmos. But nobody has detected an individual relic neutrino directly. They carry so little energy that catching one is beyond any instrument yet built. There is a more distant possibility still. Gravitational waves pass through everything, including the fog. They do not scatter. In principle, ripples generated in the first tiny fraction of a second could still be crossing the universe, carrying information from an era no light can ever reveal. If we could detect that background, we would be observing the universe at an age of something like a trillionth of a trillionth of a trillionth of a second. Enormous efforts are underway to find it, mostly by searching for a faint twist it would have imprinted on the oldest light. Nothing has been confirmed, but the wall we hit tonight is a wall for photons only. There are other windows, and they are not yet open. But what happens when you ask where the center is? There is no center, and the reason is worth sitting with, because it changes how the whole picture feels. Every measurement we make says the universe looks the same in all directions and is built the same way everywhere. On large scales, one region is much like another. There is no special location, no preferred spot, nothing that could be called the middle. But then, why does the observable universe look like a perfect sphere with us at the center? Because it is a sphere centered on the observer, and every observer has their own. Your observable universe is the region from which light has had time to reach you. That is a sphere around you, by definition. Someone in a galaxy 10 billion light-years away has an equally valid sphere centered on themselves. The two spheres overlap substantially, but they are not the same. Their sphere includes regions we will never see and excludes regions we can. There are as many observable universes as there are places to stand. This is the same as standing on the ocean. The horizon forms a perfect circle around you, and you are exactly at the middle of it. Walk a mile, and it moves with you. Nobody would conclude they were at the center of the sea. We are not at the center of the universe, astronaut. We are simply at the center of our own view of it. That is the only kind of center a horizon can have. And yet, there's more to this story, and it explains something you have seen every night of your life. Why is the sky dark? The question sounds childish, and it is one of the most profound in astronomy. Suppose the universe were infinite, eternal, and evenly filled with stars. Then every line of sight, extended far enough, would eventually strike the surface of a star. Every point on the sky would be as bright as the surface of the sun. Night would not exist. The whole sky would blaze. More distant stars appear fainter, but at greater distances there are proportionally more of them, and the two effects cancel exactly. The conclusion is unavoidable, and it troubled astronomers for centuries. The sky is dark. So at least one of the assumptions must be wrong. We now know two of them are. First, the universe is not eternal. It began 13.8 billion years ago, which means only light from within our horizon has had time to arrive. Most lines of sight run out of time before they run into a star. Second, the universe expands. Light from very distant sources is stretched and weakened, and the most distant regions are receding so quickly that their light is dragged into wavelengths our eyes cannot register. And here is the elegant part. Every line of sight does eventually end on something bright. It ends on the wall of light, the surface of the glowing early universe, which does surround us completely in every direction. That surface is genuinely blazing, but its light has been stretched by a factor of 1100, cooling it from a brilliant glow into faint microwaves. The sky is not dark because it is empty. It is dark because it has cooled. The journey continues to a fact that sounds impossible. Some galaxies are receding from us faster than the speed of light. This is true, well established, and does not violate relativity in any way. The rule in physics is that nothing can move through space faster than light. Expansion is not movement through space. Distant galaxies are essentially stationary relative to their own surroundings, drifting only slowly, exactly as we are. What increases is the amount of space between us. Add up enough expanding space, and the total separation can grow faster than light travels, without anything locally exceeding the speed limit. The distance where recession reaches light speed is around 14 billion light-years. Beyond that, every galaxy is receding superluminally, and there are a great many of them. Most of the galaxies in the observable universe fall into this category, which raises an obvious objection. If they are receding faster than light, how do we see them at all? The answer is genuinely subtle. A photon emitted toward us from such a galaxy does initially lose ground. The space it must cross is growing faster than it can cross it. It gets carried backward in terms of distance from us. But that boundary is not fixed. As the expansion rate changes over cosmic time, the distance at which recession equals light speed can move outward. A photon losing ground can eventually find itself inside the region where it can make progress. And from there, it slowly, painfully wins. Some of the light reaching us tonight spent billions of years falling behind before it began to gain. Now, let's go deeper into the part of this story that is genuinely melancholy. There is a second horizon, and it is more restrictive than the first. The one we have discussed so far concerns what we can see. There is another that concerns what we can ever reach or ever hear from again. Astronomers call it the cosmic event horizon because The expansion of the universe is accelerating. The distance between us and remote galaxies grows at an increasing rate. For sufficiently distant galaxies, that growth is now permanent and unbeatable. A signal sent from us today, traveling at the speed of light forever, would never arrive, and nothing they emit from now onward will ever reach us. That horizon sits at roughly 16 billion light years. Compare that with the observable universe at 46.5. The gap between those two numbers is the sad part. Nearly everything we can see is already beyond our reach. Estimates suggest that around 94% of the galaxies currently visible are permanently unreachable, even in principle, even with unlimited time and a spacecraft traveling at light speed. We can photograph them. We can measure their chemistry, their motion, their age. We can never go, and we can never send word. And the situation is worsening. As the expansion accelerates, galaxies cross that boundary one by one and are lost, not destroyed, simply removed from any possible contact forever. The observable universe is the largest it will ever be in terms of what we can influence. Everything from here is a slow contraction of what is possible. But what happens when we ask how big the whole thing is? The observable universe is a well-defined quantity. The universe is not. The honest answer is that we do not know, and there is a fundamental reason we may never know. Our horizon limits what evidence can reach us, so anything beyond it is invisible by construction. But we can constrain the possibilities. The key measurement is curvature. Space can, in principle, be curved on the largest scales, and different curvatures imply different geometries. Positive curvature would make the universe finite, closing back on itself like the surface of a sphere. Zero curvature means it is flat, extending without bound. Curvature affects how large distant features appear, and the oldest light provides a superb ruler for measuring it. The result is that the universe is flat to within a very small margin of error. If it is exactly flat and connected in the simplest way, then it is infinite and always has been. Infinite at the moment of the Big Bang, too, which surprises people. The Big Bang was not an explosion at a point in a pre-existing void. It was a hot, dense state everywhere at once, in a space that may already have been endless. There is a loophole. A flat space can still be finite if it wraps around like a video game screen, where leaving one edge returns you at the other. If the universe wrapped on a scale smaller than our horizon, we would see repeated patterns in the oldest light, the same structures appearing in different directions. Astronomers searched carefully for those matching patterns. They found none. Whatever the true shape, it is at least as large as everything we can see, and quite possibly hundreds of times larger. Now, let's go deeper into what we are quietly assuming about the rest. When cosmologists describe the universe beyond our horizon, they generally expect more of the same. More filaments, more voids, more galaxies, obeying the same physics, made of the same ingredients. That expectation rests on an assumption called the cosmological principle. It holds that our location is not special and that the universe is broadly the same everywhere. The assumption is reasonable, and it has passed every test we can apply. Within our horizon, the universe genuinely does look uniform on large scales. There is no sign of an edge, no gradient, no direction that behaves differently from any other. But notice the limitation carefully. Every one of those tests was performed inside our horizon. We are confirming uniformity across the region we can see, and then extending the conclusion to a region we cannot. That is not a proof. It is an extrapolation, and it is untestable by construction. There are ideas in modern cosmology in which the assumption fails badly. Some versions of rapid early expansion suggest it never fully stopped everywhere, and that our smooth, well-behaved region is one patch among many, with different conditions elsewhere. Others allow the density or even the physical constants to vary across scales far larger than we can survey. None of this can be examined directly. The horizon is not a practical obstacle that better instruments will eventually overcome. It is a boundary on what evidence can physically reach us. So the honest summary is this: we assume the universe does not become strange just beyond the point where we stop being able to look. It is a sensible assumption. It is also permanently an assumption. And yet, there's more to this story, because there is a serious problem hidden in the uniformity. Look at the oldest light in one direction and measure its temperature. Then look at the exact opposite direction and measure again. The two match to within about 1 part in 100,000. That should be impossible. Those two patches sit on opposite sides of our horizon. Light from one has not had time to reach the other, and never did in the entire history of the universe. They have never exchanged energy or information of any kind, yet they are the same temperature to remarkable precision. Things reach the same temperature by being in contact. Put a hot object next to a cold one and wait, and they equalize. But equalizing requires interaction, and interaction cannot travel faster than light. Astronomers call this the horizon problem, and it demands an explanation. The leading one proposes that in the first tiny fraction of a second, the universe underwent an episode of extraordinarily rapid expansion. Not the gentle stretching we see today, but a violent exponential burst. In that picture, the entire region that became our observable universe began as a patch smaller than a proton. It was small enough to be in thorough contact, so everything in it evened out completely. Then, in far less than a trillionth of a second, that patch was blown up to macroscopic scale. Everything we can see was once close enough to touch. That is why the sky is so uniform. Now, let's go deeper, because that idea does more than solve one puzzle. Rapid early expansion explains the flatness as well. Take any curved surface and enlarge it enormously, and any small region of it becomes indistinguishable from flat. The ground beneath your feet feels flat for exactly this reason. It also explains why the universe is not perfectly smooth, which matters enormously, because a perfectly smooth universe would contain nothing at all. At microscopic scales, quantum fields are never entirely still. There are always tiny fluctuations appearing and disappearing constantly. Under normal circumstances, they are far too small to matter. But if space expands violently enough, those fluctuations can be stretched to enormous size before they have a chance to vanish. Microscopic quantum jitter, inflated to cosmic proportions and frozen into place. Those stretched fluctuations became the slight variations in density that we still measure in the oldest light. Gravity then spent 13 billion years amplifying them into filaments, galaxies, stars, and planets, which leads to a genuinely startling claim. The arrangement of every galaxy in the sky and the position of the Milky Way, and ultimately the existence of the Sun and Earth, may trace back to random quantum fluctuations in the first fraction of a second. The evidence is indirect but substantial. The theory predicted specific statistical properties for those variations before they were measured precisely and the measurements matched. It is not proven. Physicists continue to debate the details, and the mechanism remains unidentified, but it currently explains more than any alternative. But what happens in the very far future? The horizon story has an ending, and it is a quiet one because expansion is accelerating. Distant galaxies will continue crossing beyond the event horizon. Their light will stretch, dim and slow, redshifting toward wavelength that no instrument can register. One by one, over tens of billions of years, they will fade from view. Eventually, only the galaxies bound to us by gravity will remain, our own local group, by then merged into a single large elliptical. Everything else will be gone, not moved away, but genuinely unobservable. The oldest light will fade too, stretched until its wavelengths become impossibly long and its temperature effectively zero. Consider what that means for anyone living then. They would look up and see stars, and nothing beyond. No other galaxies. No redshift to measure, because nothing external would be visible. No ancient background glow, because it would have vanished. Every observation they could make would suggest a single island of stars in a static, eternal void. They could do excellent science and arrive at a completely wrong picture with no possible way to detect the error. The evidence for the Big Bang, for expansion, for the entire history of the cosmos is temporary. It is available now. It will not always be. We happen to live in a window when the universe is still legible. Late enough for the light to have arrived and for someone to be here to read it. Early enough that the evidence has not yet slipped away. Take a quiet moment to reflect on what this means, astronaut. There is a particular feeling that comes with all of this, and it is not quite sadness. We have spent tonight establishing limits, a boundary at 46 billion light years, a wall of light we cannot see past. 94% of visible galaxies permanently out of reach. An unknown quantity of universe beyond our horizon that we can never examine. A future in which even the current evidence disappears. It sounds like a list of failures. It is the opposite. Every one of those limits was discovered. Nobody handed them to us. A species confined to a single small planet, working with light collected in mirrors, measured out how far sight extends, established that space itself expands, calculated conditions in the first fraction of a second, and identified precisely which parts of reality are permanently closed to it. Knowing exactly where the boundary lies is not the same as being trapped by it. It is a form of understanding, and a fairly extraordinary one. And there is something restful in the shape of the answer. There is a limit. There is a definite point past which nothing can be learned, no matter how hard anyone tries. Not everything is available, and no amount of effort will change that. You are inside a horizon tonight. So is everyone who has ever lived and everyone who ever will. It is 46 billion light years wide, and it holds 2 trillion galaxies, and it is more than enough. We drift homeward now, inward, through the layers, past the wall of light, past the first galaxies, past the filaments and the clusters and the quiet dark between them. The Milky Way appears, then the sun, then a small blue point turning slowly beneath us. Nothing out there has changed tonight. The horizon sits exactly where it always has, moving outward a little as light continues to arrive, letting go of distant galaxies at the other end. It will keep doing that whether anyone watches or not. The sky above your roof is the same sky. Faint microwaves from the beginning of everything are falling through your ceiling right now, passing through you, arriving after 13.8 billion years of travel and delivering the last of their energy in your room. They have come a very long way to be here. Close your eyes now. Let the distances go. There is nothing out there that needs you tonight, and nothing beyond the horizon that will not wait. Mission complete, astronaut. The stars will wait for you. Good night.